Now that we've talked about the basics of graph transformations, translations, left, right, up or down, reflections across the x-axis or the y-axis, vertical stretches and compressions, and horizontal stretches and compressions, we want to take a look at the homework problems and see how to apply this information. Let's start with number 1. Let me share my screen with you. And let's get started. We have a lot of homework problems to look at. We probably won't do them all, but we'll do enough that you get a good feel for it. The unfortunate part about this particular homework set is there's not a lot of work to show. A lot of the work is simply done inside your head. This is good and this is bad. This is good because it means the problems are generally shorter. This is bad on an exam because it means there's not much work to show. And when there's not much work to show, it's harder to get partial credit. The more work you show, the more partial credit you get. So on an exam, you'll want to write down everything you know and everything you think you know. And you also want to make note if you don't know something, why you know something is wrong, but that you don't know how to fix it. That's okay too. Knowing that you know it's wrong gives me more information of where your knowledge lies, and I can give you partial credit. Let's take a look at problem number 1. In problem number 1, we have let f of x equal the square root of x, our toolkit function. Find g of x, the function that is f of x shifted up 3 and left 7. Up 3 affects vertical, so it affects y, so it must be outside of the square root. Left 7 is a horizontal change, so it affects x. Shifts left and right are addition and subtraction. So we're going to write our square root function and remember to put the vertical shift outside the square root and the horizontal shift inside the square root. So now we have the square root of something. Square root of what? Well, x. We're starting with the toolkit function square root of x. So we're going to have an x. Now what would make it go left 3? Left to me says negative, but because it's inside affecting x, it's got to be the opposite. So it's got to be plus. And that would make it plus 7. Now, to make it go up 3, I need to go outside of the main operation. So I get outside of the square root and I tell it to go up 3. Because it affects y, it does what I think it should do. Plus should make it move up, minus should make it move down. Let's check our answer and see how we did. We'll want to make sure that we're looking up here at the visualization of it to make sure that this does look like what we intended. And we've got it correct. Let's move on to problem number 2. In problem number 2, we're starting with a different toolkit function, one that we didn't really talk about. It's the basic rational function. We can look at the basic rational function if we look over here at common functions to memorize. Rational functions are here. Let's see if the rational function shows up on our second list. This is the basic rational function that you'll see right here. This one is 4 over x, but ours is 1 over x. Again, it sort of has this boomerang shape in quadrant 1 and a boomerang shape in quadrant 3. That's what our toolkit function looks like. We want to find the transformed function that shifts it down 10 units and right 6. Now we have to think about what the main operation is. The main operation is the division. So to shift it down 10, I need to be outside the main operation and have a plus 10. To be inside the main operation will affect the horizontal change left or right. So to do that, I need it to shift right 6. Well, I know my function is 1 divided by x. And then in order to get it to shift to the right, well, I would think right would be plus 6, so it must be minus 6 because it's affecting x. But I need to put parentheses around the denominator so that it knows that this is all inside of the fraction. Missed my parentheses. This gives me 1 divided by x minus 6 plus 10. In other words, what I'm thinking the problem should look like is 1 over x minus 6 plus 10. Does that do what it's asking? Shift down 10 units. Uh-oh, down, that's outside. Down should be minus. So this should be a minus 10 on the last part. I fixed that error. What about the shift right 6? If I go right 6, that would be the opposite to what I expect because it's inside the main fraction. Now this is going to shift it to the right by putting minus 6. It looks, I think, like what I'm expecting the answer to be. So let's check. Make sure that this representation matches the one you have here, and it is correct. Let's move on to number 3. Number 3 is another problem where there's really nothing to show. You're just clicking the answers you think are correct. What happens to the toolkit function f of x if you replace it with f of x minus 3? The minus 3 is inside the main operation, and it's being subtracted, which is just shift left or right. Well, which is it? Minus, I would normally think, would make it go left, but it's inside the main operation, so it does the opposite and goes right 3. Click on right 3. What about a transformation that replaces the toolkit function with f of x plus 3, the quantity, and then minus 10? The minus 10 will definitely shift it down 10. So I know it's got to be one of these last two. The plus 3 is going to do the opposite to what I expect. So instead of going right 3, it'll go left 3. Left 3, down 10. Let's check. Perfect. Moving on to number 4, we have a similar kind of problem. We have our toolkit function f of x, even though they didn't tell us what it is, and they want to know what the effect of replacing it with f of x plus 7 is. Now keep in mind, these replacements are not equal to the original toolkit function. They're transformations of that function. This would normally shift left or right, and because it's plus, it actually goes left 7. F of x minus 7 is inside the main operation, and it's subtracted, which means left or right. And since it's subtracted, it does the opposite and goes right 7. That's the second or the fourth choice. Then the plus 10 should move it up 10, which is the second choice. Looking at number 5, we have the same kind of problem. I'm going to leave this one for you to try at home. And the same on number 6. And 7. Uh-oh, number 8 is a little bit different. On number 8, we're talking about increasing and decreasing. What does that mean? And they're talking about intervals. Increasing are the x values over which the function is going up as you go from the left side to the right side. Let's take a look over here and describe what happens on the toolkit function x squared. The normal graph of x squared, remember from our toolkit function, and no, I can't draw very well, so you'll have to use your imagination, normally goes through 0, 0, right 1, up 1, left 1, up 1, right 2, up 4, and left 2, up 4. This is our toolkit function for the parabola x squared. What do we mean by increasing and decreasing? Remember that you read a graph the same way you read interval notation, left side to right side. When I'm on the graph and I'm going from the left to the right, I would say it was going down in y value when x is from negative infinity until I reach 0. So I would say that it's decreasing, talking about the y value, when the x value is from negative infinity up to 0. In other words, y decreases when x is in this range. What about increasing? Again, you have to go left to right. Whether it's uphill or downhill depends on the direction you travel. The direction in mathematics is left to right. From the left to the right, what happens from 0 to infinity? Put your cursor on the graph and move it. It's going up. The y value is increasing, while the x value sits between 0 to positive infinity. So we would say it was increasing on the interval from 0 to infinity. That means that y increases when x is in the interval from 0 to infinity. Notice that the interval notation refers to the x values, but the increasing decreasing is actually referring to the y values. It's a little confusing. Now let's go ahead and put our values over here. Let's look at the transformed function and see what we can think about what's going to happen. What they've done to my toolkit function, x squared, is they have shifted it with a +3 and a +1, and they've stretched it with an outside 2. Let's write down the transformed function and describe the pieces. F of x, which was x squared, got transformed, which is why I put an arrow and not an equals. And now it looks like 2 times x plus 3 quantity squared plus 1. What does the +3 do? It's inside the main operation. The main operation is the square. The square, after all, is what's present in the toolkit function and gives it its typical shape with the typical 5 points. That means the quantity squared is the main operation. The +3 is inside of it, so it affects x. Since it's a +3, it does the opposite and actually moves left 3. The 2 is outside the square. It gets done order of operations after the square. So because it's outside, it affects the y. Since it's 2 times that, not added or subtracted, it's not a shift, it's a stretch or compression. Multiplying by a number bigger than 1 stretches for y, and a number smaller than 1 compresses. This would be a vertical stretch by a factor of 2. What about the +1? The +1 also happens after the square, which is the main operation. The main operation is like the notation. Since it happens on the outside, it also affects y. And this is going to do what we expect and shift it up 1. Now let's think about what's happened to our toolkit function. When we're looking at the graph right here, each of the values got shifted and we had a vertical stretch. So what happened was the x's moved to the left 3, the y's moved up 1, and also got stretched by a factor of 2. Let's take a look now at our graph on Desmos and see what effect that has on the graph. Let's take a look at the original graph, which is x squared. That's our toolkit function. I've plotted the basic 5 points that you can see here. Now let's put on the transformed graph. The transformed graph is 2 times the quantity x plus 3 squared plus 1. Now what happened to the 2, 4? First thing that happened was the x coordinate got shifted to the left by 3. So 2 minus 3 would put us at -1, which is on this line right here. Then the y value got multiplied by 2, so it became 8. And then it had 1 added, so it became 9. That would put us at -1, 9, which would put us right about here. If I can get it right on the spot. And of course, I cannot. I did it just, there it goes, -1, 9. What about the point 1, 1? Again, the x coordinate gets shifted to the left first because it's inside the main operation. 1 minus 3 would put it at -2, which will be along this line here. The y value gets multiplied by 2, so it becomes 2. Then you add 1, so it becomes 3. That's going to be at -2, 3, which should be right here. This is what happens to each of the points. Let's take a look at another one of the points and see what happens to it. How about -1, 1? The point -1 gets shifted to the left 3, so it becomes -4, which is along this line. The y coordinate gets doubled first to become 2, then has 1 added to become 3. This is at the point -4, 3. I hope this makes sense to you. Let's now return to our problem and see how to answer the problem. It's asking us where it's increasing and where it's decreasing. The 2 is applying a vertical stretch factor, but it doesn't affect the increasing and decreasing. What affects the increasing and decreasing is the shifts from the left and the right. That changes where the vertex of the parabola is, that lowest point. Let's look at the graph again. Notice that the point 0, 0, which is where it stopped decreasing from -infinity to 0 and started increasing from 0 to infinity, took place. When we shift and transform the graph, we change the place where it does this change from decreasing to increasing. Again, the x coordinate gets shifted left 3, so it goes to -3. The y coordinate gets doubled, which is, of course, 0, 0, which goes to 0. 2 times 0 is 0. And then +1 shifts it up 1. So it ends up here at this point, -3, 1. That means that it's decreasing as x moves across. The y value is going down while x goes from -infinity up to -3. And then it's increasing from -3 to infinity. Again, when we give the interval, we're always talking about the x values. The y values are decreasing, but it's over the x range. It's increasing from -3 to +infinity. And again, the values inside of the interval are x values. We're talking about the y values increasing or decreasing, but we're giving the x values where that happens. Now let's put our answers in over here. Notice that the order is different to what I have written down here. We'll want to make sure that I put in the correct one in the correct place. I have increasing from -3 to infinity. Oops, wrong character. -3, infinity. And then the next one is decreasing from -infinity, INF, up to -3. Let's check our answers and see how we did. We always want to check the part where it gives the answer preview to make sure that this picture matches what I have on my handwritten work. On an exam, I will be checking the handwritten work on each problem. You need to be sure that you're following the directions for the write-ups, which include numbering the problem and drawing horizontal lines between them. Do not double column, as that absolutely drives me bonkers. A little wasted space is a good thing for thinking and neuroscience. Let's take a look now at our next problem. On number 8, we're to look at this equation, y = x + 3 squared + 1. Without using Desmos or some other technology, how do we know what this graph would look like? Let's go ahead and write down the equation and describe what's happened to the equation. Our equation is y = x + 3 quantity squared + 1. The square is what makes it look like its typical graph. The toolkit function is x squared. What's happened to the graph of x squared is that it's been shifted left or right, since this is inside the main operation, which is the square. It's a plus, which means it did the opposite and went left 3. Remember, things inside the main operation or the notation affect x, and they always do the opposite to what you expect. This +1 is outside the square, so it affects y and does what I think it should do, which moves it up 1. So the main point of the parabola, which of course occurs here at the bottom, and that wasn't a very good graph, at 0, 0, got shifted left 3, up 1. Where would it end up? The point 0, 0 got transformed. It's not equal to the other point, but it changed and became -3, 1. Let's look at our pictures and find the one that has a vertex at -3, 1. There's no negative on the outside being multiplied by the square and no negative being multiplied by the x, so it's not been reflected over either axis. It should still be an upward opening parabola, but shifted so that the vertex is at -3, 1. This is shifted to the right, which is the wrong direction. This one is shifted left 3, down 1, but again, it should be up 1. This has been shifted to the right 3, which is the wrong direction, but this has been shifted left 3 and up 1. It must be D. Looking at this problem right here, we can see that we have several changes going on. We have a negative on the outside of the square, which means it's going to affect y. And because it affects y, it's a vertical reflection, which is going to fold on the x-axis. I know it's kind of opposite, but again, think of a vertical folding. Then we have a -1 inside the parentheses, which will be a shift left or right. Because it's -1, it's actually going to go to the right one. And then we have a +2, which is going to shift it up 2. Let's write that information down and note where our vertex has gone on the toolkit function. This was part A, and this is part B. This is going to reflect across the x-axis. It's a vertical reflection. The 1 is being subtracted inside the main square. Because of that, it's inside the notation, which means it's a shift left or right. A minus does the opposite to what I expect, so it actually went to the right one. The +2 is outside the main operation, the square, and so it does what I expect and affects y. Y controls up and down, so this goes up 2. What's happened to my typical toolkit vertex at 0, 0? It's been shifted right 1, up 2. That means it's at 1, 2, but instead of the graph looking like this, it's been reflected so that it opens down. So instead of a parabola opening up, we have a parabola opening down. Let's look now at the pictures and see if we can find the one with the vertex at 1, 2. This one has been shifted to the left one, and I want right 1. This is also shifted left 1, so it can't be correct either. Both of these have a shift right 1, but only D has a shift up 2. It's got to be choice D. I'm going to leave you to do the next toolkit function. This is very similar to the previous problem that we've drawn, and we have one here which looks the same as well. One thing that I do want to note on this particular problem, which is number 10, is on part B. Let me write down what this is so that you can be sure not to miss this. The toolkit function, of course, is going to be the square root of x. Our transformed function is 1 minus the square root of x minus 3. The toolkit function looks like the upper arm of a sideways opening parabola, or someone swimming and doing the American crawl with their arm coming out of the water. When I look at this one, notice first off that it's written in an order that I'm not expecting. The 1 is outside the main operation, which is the square root, so it affects y. It's okay to rewrite this equation as negative times the square root of x minus 3 and then plus 1. That may make it make a little more sense to you. The negative is going to reflect it across the x-axis, a vertical fold. So this is a vertical reflection. Remember that the Toolkit function looks like the upper arm of a sideways opening parabola. So when it's reflected, it will look like the lower arm of the sideways opening parabola. The minus 3 is going to shift it. In this case, it's going to go right 3 and do the opposite to what we expect because it's inside the main operation. The plus 1 is now outside. It was outside here as well. It just didn't look right to me. So I changed the order of the terms, and this moves it up 1. I'll leave it to you to figure out which of the curves is the correct one. In problem 11, we're asked to find the equation for the graphed function by using the transformations based on the Toolkit function square root of x. How do I know that this is square root of x? I've memorized it. There's really no other way around it. You're going to have to memorize what the basic Toolkit functions look like and their basic points. Let's put the square root of x's basic points down so that we can be sure we know what's happening to the Toolkit function. This is problem 11, and my Toolkit function is the square root of x. This is the common function that I've memorized. What does it look like when I graph it? It starts with the sideways vertex of 0, 0. Then it moves right 1, up 1 to give me the point 1, 1. Then it moves to the right 4 and up 2 to give me the point 4, 2. I could go further and I could have the next point be 9, 3. But that's probably enough to have those 3 points. Now let's take a look at the graph that we see here in the picture and try to figure out what's happened to it. The first thing that we want to find out is whether or not we have a stretch or a compression. Stretches and compressions take place before the shifts, so we need to know if it's got the same basic relationship between the points as our Toolkit or if they've been changed. The basic relationship between the points is from the vertex right 1, up 1, and right 4, up 2. Right 1, up 1, that looks right. Right 4, 1, 2, 3, 4, up 2, 1, 2. That looks right. Because the relationship is the same, I know it has not been stretched or compressed either vertically or horizontally. That makes it a much easier problem than it could have been. In other words, there is going to be no number multiplied by the square root and no number multiplied by the x under the square root. Instead, we'll have a number possibly added or subtracted outside the square root for an up-down movement, and a number added or subtracted to x under the square root for a left-right shift. Now we look at the vertex point here. It starts in the Toolkit at 0, 0. Where did it end up? It ended up at left 2, down 1. That's negative 2, negative 1. Let's go ahead and write that down. The vertex point went left 2, down 1, and ended up at negative 2, negative 1. Left 2 can be accomplished by transforming our Toolkit function into a function where f of x is equal to the square root of x plus 2. Remember, when it's under the main operation, it does the opposite to what you'd expect. I think plus would move it to the right, so of course it moves it left. And then down 1 is outside the main operation, so it does what I expect, and I get a minus 1. I almost put a 2 again. I think it should be the square root of x plus 2, the quantity, then minus 1. Let's test and see. Move outside the notation to put the minus 1. and then check your answer. Make sure that you check the answer preview to make sure that this matches what you have over here. When you make a mistake, that's actually most common mistake to make. It's just to type in your answer wrong, not to actually work it wrong, but to type it in incorrectly. Check that first. We're going to repeat the process now on this equation here. This is our toolkit function, x squared. What are the points on that graph? Well, we know it starts with a vertex at 0, 0, and we have a parabola which opens up on both sides. It has points 1, 1, right 1, up 1, and negative 1, 1, left 1, up 1, right 2, up 4, which is 2, 4, and left 2, up 4, which is negative 2, 4. We need to make sure that there was not a vertical stretch or compression or a horizontal stretch or compression by checking the relationship between the points. Let's locate the vertex on this one over here. The vertex looks like it's been shifted from the origin, left 2, down 3. That means the vertex ended up at negative 2, negative 3. Now let's take a look at the relationship between the points and the vertex. Is it still right 1, up 1? Yeah, that checks. Left 1, up 1? Yeah. Right 2, up 4? 2, 3, 4. Yes. Left 2, up 4? 1, 2, 3, 4. Yes. Then there's been no horizontal or vertical stretch or compression. We only have to worry about shifts left, right, and up, down. Now we're going to look at this one. Notice that there's been no reflection because it still opens up. So we have no negative multiplied on the outside of the square or a negative multiplied by x on the inside. All that's happened is that we have picked it up and put it down somewhere else. In order to get it shifted to the left, we're going to transform our x and write f of x is equal to x. And now it went left 2, so we put plus 2, and down 3, so we put minus 3 outside the square. Let's enter our answer and check. Remember to use the caret symbol for the power, which is found on the 6 button on your keyboard. Let's move on to problem 13. Problem 13 is the same relationship as the previous 2 problems, so I'll leave it to you to do at home. Now we want to talk about something slightly different, which is even, odd, and neither. What does even, odd, and neither refer to? An even function is one that is y-axis symmetric. Our toolkit function of x squared and our toolkit function of absolute value of x are both even functions. Let's take a look at the toolkits and see why they're even functions. I'll call this one g of x to distinguish it from f. Now, why do we call these y-axis symmetric? If I were to fold on the y-axis, making the y-axis the crease of the paper, this side would lay on top of that side. That's what we mean by y-axis symmetric. However, graphing is not a great way to determine something because you can never see 100% of the graph. Graphs go forever, so we can only see a portion at a time. How can we do this algebraically? For an even function, what we write is that f of negative x is equal to f of x. In other words, if I change the x to become a negative x, it doesn't change the y value, it stays the same. Let's test that on our toolkit functions. If I do f of negative x, I get a negative x quantity squared. Remember to open up the hole and to substitute in what you have. That means that the negative goes on the inside and the 2 is outside. A negative squared is a positive, so this leaves me x squared. But x squared was the original function f of x. This proves algebraically that it's even. Let's look at g of x and do the same thing. What would I get for g of negative x? Again, I open up empty parentheses to replace the letter x, the variable, and then I substitute a negative x on the inside. The absolute value of a negative x is equal to x. Well, the absolute value of x, because I can split the negative 1 off of the x, and this would give me the absolute value of x. But that, of course, is just g of x as it was originally stated, so that g of negative x is equal to g of x. And I've proved algebraically that these are even functions. Let's take one that's not even and see what happens when we substitute negative x for x. Let's look at the toolkit function, h of x equal to 1 over x. This is a rational function. Over here, it looks like this right here and this right here. 2 boomerangs, one in quadrant 1 and one in quadrant 3. If I were to take this function and I were to replace x with negative x, what would happen? Open up empty parentheses in place of the variable and substitute negative x inside. This gives me 1 over negative x. And since fractions allow us to move the negative around, I can write this as negative 1 times 1 over x. This is the same as writing negative 1 times the original, which is h of x. That is not what I had in the beginning for the first 2 examples. In this case, h of negative x gives me negative h of x, which is a different kind of symmetry. This is not an even function because it didn't give me back h of x. What it gave me instead was the opposite of h of x, or negative h of x. This is called an odd function. And we say that it has origin symmetry. Now, what does it mean to have origin symmetry, and how can you fold on the origin? Well, you can't exactly fold on the origin. What you do instead is you fold twice, once on the x and once on the y. It doesn't matter which one you fold on first, you just want to fold on both. Let's take an example and let me show you what would happen if I were to fold the part in quadrant 1 down onto this part in quadrant 4. This would make a mirror image of it like this if I were to first fold on the x-axis. And then if I were to fold on the y-axis, do you see how the pink dotted line would lay upon this part here in quadrant 3? That's origin symmetry. A double fold makes it line up. That's called an odd function, and it's origin symmetry. And that means that if you replace x with negative x, you don't get the original function, but you do get the opposite of it. Now, what about something that's neither? Let's take something that has no symmetry and let's see what happens to it. Let's take the function f of x is equal to x squared. No, not that one. Let's take x minus 1 squared. Now, what's happened to this? Because of the minus 1 inside the square, it's been shifted to the right one. That means that the origin point is the vertex. Then we go right 1, up 1, which puts it at 2, 1, right 2, up 4, which puts it at 3, 4. We go left 1, up 1, which puts it at 0, 1. and we put left 2 up 4, which puts it at -1, 4. I'm not very good at drawing, and I don't have a very steady hand. It's a good thing I'm not a surgeon. When we're looking at this, though, notice that if I were to fold on the y-axis, this part would not lay on this part. It would not match up exactly. You can think about these parts having ink on them or paint on them, and then folding and seeing where the imprint would go. If it goes exactly on the other part, it's symmetric, but it wouldn't, so it's not symmetric. What about a double fold? Well, a double fold won't help. There's nothing down here. It's still not going to line up. This function has no symmetry at all. So we would say it's neither. It has symmetry of a kind, but that's symmetry to itself. And that's symmetry around a line that goes through the vertex. But that's not y-axis symmetry, and it's not origin symmetry. It's not even, and it's not odd. It has symmetry to itself, but not to the y-axis and not to the origin. So it's neither even nor odd. Let's now take a look over here at problem number 14. In problem number 14, we have the transformed function f of x equals -9x squared. We want to know, is it even, odd, or neither? Graphing is not a great way to do it because we can never see 100% of the graph. However, I can do it algebraically. I replace the x with -x and test to see what I get. If I get -9x squared again, it's even. If I get the opposite of that, 9x squared, it's odd. If I get something totally different from those two, it's neither. In this case, I rewrite the problem and I open up an empty set of parentheses in place of the variable x. And then into the parentheses, I substitute -x. When I square the -x first, the double negative becomes positive x squared. Note that you cannot multiply this negative by this negative because you have to square first. Order of operations must be followed. I like to write it like this. This is parentheses, but it really means grouping symbols. That might include anything in parentheses or anything inside of an absolute value or anything in the numerator only or anything in the denominator only. Those are grouped places. E stands for exponents. Exponents have to be done after the grouping, but before any multiplication and division. Multiplication and division are done in order from left to right, whichever one you hit first. Yes, there is an order, left to right, whichever you hit first, multiplication or division. And then, of course, we have addition and subtraction, again, left to right. I don't ever have students mess up the AS level, but it is possible, and I do see students messing up the MD level. Remember to go from left to right when you're multiplying or dividing, and there are no parentheses to group. In this case, I square the -x first to get x squared. Then I multiply by the -9 to get -9x squared. But that's what I originally had, f of x. That means f of -x is equal to f of x, which means that this is an even function. Over here on the work, it wants to know what f of -x turned out to be. It turned out to be -9x squared. So I type that in. Remember to use the caret for the power. F of x then is equal to -f of -x. Therefore, f of x is even. Now, notice, oh, wait a minute. F of x is equal to f of -x. I typed on the wrong one. And therefore, f is even. All right? They're not opposites. They truly are the same thing. Now we can check our answers and move on to the next problem. In the next problem, we have 1 over x plus 6x. We want to know if it's even, odd, or neither. We replace x with -x. That's going to open up empty parentheses everywhere that the x originally appeared. Then we substitute negative x in place of the parentheses. Then we rewrite without the parentheses, which would give me a negative 1 over x minus 6x. Now, the confusing part on this one is that it's got the double negative, but I can factor the negative out by dividing both terms by negative, and that leaves 1 over x plus 6x. But that's the original expression, so I have a negative times f of x. That means f of negative x is equal to negative f of x. Another way of writing that is to have f of x equal to negative f of negative x, where I simply move the negative from this side of the equation to that side. It means the same thing. Coming over here, we can write it in either form, this form or this form. I'm going to write it in this form here. I have a negative 1 divided by x, which it will know to do before the subtraction, minus 6x. That is what f of negative x gave me. F of x is equal to the opposite of f of negative x. They're opposites of each other, and therefore it is an odd function. Let's take a look at the next problem. In the next problem, we have x minus 10 quantity squared. We have f of x equal to x minus 10 quantity squared. When we're looking at this and we're trying to determine if it's even, odd, or neither, we replace the variable x with empty parentheses, and we substitute negative x in its place. I'm going to have big parentheses for the square and little parentheses replacing the variable x. Then I substitute negative x into the inside. I can drop the inner set of parentheses because there's nothing between the two sets of parentheses. No negative, no number. This gives me negative x minus 10 quantity squared. However, that does not look like the original, which was a positive x minus 10. The minus 10 is the same, but the x is different. It's not the original, and it's not the opposite of the original either. That means that this one is neither. I'll leave you to put the answers in, and then you can see what the result will be. Let's take a look now at problem number 17, which is more of an inspection problem. When we're looking at 17, it says to describe again how the given equation represents a transformation of the function. So we have some toolkit function and we're transforming it. A negative on the outside is affecting the y. So this is a vertical reflection across the x-axis. Remember, when you fold vertically, you're folding on x. That becomes a reflection across the x-axis. Now let's look at f of negative x. The negative is inside the parentheses and multiplied by the x, not added or subtracted. Because it's multiplied, it's going to be a reflection. Because it's inside, it's got to be a horizontal reflection. When we fold sideways, we're folding on the y-axis. So that is a reflection across the y-axis. When we look at the next problem, 2 times f of x, the 2 is outside the notation, so it's a vertical change, and it's multiplied, so it's a stretch or compression. For a number larger than 1, it becomes a stretch. This is a vertical stretch by a factor of 2. The 1/4 is also outside the notation, so it's a vertical stretch or compression, but the number is less than 1, which means it's a compression. This is a vertical compression by a factor of 4. The y values get divided by 4. On problem number 19, we have changed our toolkit function and we've replaced x with 9x. Because the 9 is inside the notation, it's affecting it horizontally. It's multiplied by x, so it is either a compression or it's a stretch. But because it's affecting horizontal, it does the opposite to what we expect. The number is bigger than 1, so I would expect a stretch, which must mean it's a compression by a factor of 9. This is a horizontal compression by a factor of 9, meaning that each x value gets divided by 9. On the second one, we have f of 1/3 of x. Again, it's multiplied by x, so it is a horizontal stretch or compression. It's being divided by 3 or multiplied by 1/3, a number less than 1. So I would normally expect a compression, but because it's affecting horizontal, it's got to be the opposite and be a horizontal stretch. Now let's look at some combinations of effects. On this problem, we have the toolkit function multiplied by 8 on the outside, which will be a vertical stretch, and by a negative multiplied by the x on the inside, which will be a horizontal reflection across the y-axis. So we have a vertical stretch and a reflection across the y-axis. On the second problem, we have a negative multiplied on the outside, which will be a reflection vertically, which folds on the x-axis. So we have a reflection across the x-axis. On the inside, we have 1/3 multiplied by the x. It's a number less than 1, which would normally be a compression, but because it's affecting x, it's going to be a stretch. So we have a horizontal stretch, and we have a reflection across the x-axis. Make sure you pick the right answers. Now we want to take a look at this problem, number 21. We're starting with the toolkit function of square root of x. We want to find the transformation of it, that is the function reflected over the x-axis, over the x. That's a vertical reflection, so it's got to be a negative on the outside multiplied by the square root, and horizontally stretched by a factor of 4. That's got to be on the inside multiplied by the x. Since it's stretched, normally it would be 4 times, but because it's inside, it's got to be a 1/4. Let's write down what we expect this one to come out to be. I think the reflection over the x-axis is going to transform the function to become a negative multiplied by the square root. The horizontal stretch by a factor of 4 is going to be the opposite to what I expect. So it'll be a 1/4 instead of a 4 multiplied by the square root of, or multiplied by x under the square root. Let's type that in and make sure that our preview matches what we think it is. Let's put the 1/4 in parentheses so it knows to divide 1 by 4 and then multiply by x. Yes, that does look like what I wrote here, and that is the correct answer. Let's now go on to this one, which says f of x has been transformed such that we have 4 times the quantity x plus 1 squared minus 2. The toolkit function is going to be x squared. Remember that x squared is a parabola, and it has the basic 5 points of 0, 0, 1, 1, excuse me, negative 1, 1, 2, 4, and negative 2, 4. What's happened to our function? Our function has been transformed. We have 4 times x plus 1 squared minus 2. The 4 is outside the square, which means it's outside the notation, which means that it is a vertical stretch by a factor of 4. The plus 1 is inside the main operation, which is the square. That's the toolkit function coming into play. The plus 1 would normally move right, so it must have gone left 1. The -2 is outside the square, so again, it affects y and does what we expect. It moves it down 2. Looking over here, we're looking for something with a vertical stretch by a factor of 4. That would be the first 4 options. Then a left shift by 1, which would be 3 or 4, and then down 2, which is the 4th one. Now we need to pick the graph. What happened to the point that was the vertex? It got shifted left 1, down 2, which means it should be at -1, -2. Looking for a vertex at -1, -2, I only have option A. Also notice that the y values have been shifted by a factor of 4, or stretched by a factor of 4 rather. What does that mean? The point that was at 1, 1 got shifted and it went left 1, down 2. So it went left 1, down 2 and ended up here, but then it got stretched. Because it was stretched by a factor of 4, it took this and multiplied by 4, which moved it up. The only possibility for a correct answer is part A. Looking at number 5, we have a toolkit function of x cubed. We've not had x cubed before, I don't think. So let's go ahead and write this one down. Our toolkit function is x cubed, which has 5 basic points on it. When we graph it, it kind of comes up, flattens out near 0, and then goes up again at a steeper rate. And it doesn't have that wobble in it. It includes the points -2, -8, -1, -1, the origin 0, 0, the point 1, 1, and the point 2, 8. It's not drawn to scale, but don't worry about that. As long as you have the basic shape right and the points correct, it's good enough. Now let's look at the transformed function, f of x equal to x cubed divided by 5 plus 2. Remember that we could rewrite this as 1/5 times x cubed plus 2. The cube is what makes it have its characteristic shape, and the 1/5 is multiplied by it and outside. Since 1/5 is a number less than 1, this must be a vertical compression by a factor of 5. It's taking the picture and squashing it this way. That would have the effect of stretching it out in the horizontal direction. There's nothing inside the cube, so it's not been shifted left or right. The plus 2 is outside, so it's also gone up 2. That means that each point has gone up 2, and then the y values were divided by 5. So the point 0, 0 should have shifted up here to 0, to 0, 2, and then divided by 5. What does that mean for our graph? Well, since it's got shifted up and then it got compressed, it looks like it would probably be this graph right here. It definitely got shifted up, not down, so it can't be A or C. Graph D is a possibility, except graph D looks like it's been stretched vertically, not compressed. Compressed would widen it out, and that must be part B. Oh, I forgot to click on the first part. We have a vertical compression by a factor of 5, which is the last 4 options, and it went up 2. That would be the first of the last 4. I'll leave you to work on problem number 24 on your own, since it's similar to the ones we've been doing. Problem number 25 is also similar, but this one has a reflection, so let's take a look at it. Our toolkit function is going to be g of x equal to square root of x. This has the basic shape starting with a horizontal parabola opening to the right with the vertex at 0, 0, and then right 1, up 1, and then right 4, up 2. This is our basic toolkit function right there. What's happened to the graph? Notice that the negative happens first. We have a reflection because we have a negative multiplied by the x thing. The negative is inside the square root, which means it's going to be a reflection across the y-axis, a horizontal reflection. So that would be one of the last 4 choices, reflect across the y-axis. Then what does the x minus 1 do? The minus 1 is going to shift it to the right 1. So we reflect across the y-axis, and then we shift right 1. Coming down here then, what has happened to our graph? When it got reflected across the y-axis, it turned it from looking like this to looking like this. And then we picked up the entire graph and we shifted it right 1, which I was hoping it would just pick up that last part, but it didn't. If I shift it right 1, then it basically looks like that. Coming down here, it looks like the first one, A, is a possibility. C and D are incorrect because they're vertical reflections across the x-axis. And B is incorrect because it moved to the left one. It's got to be choice A. I will leave you to do the next problem, number 26, on your own, since it's similar to what we've been doing before. Let's look at number 27. On 27, let's go ahead and take a look at it. Well, I guess we could look at 26. No, 27 is better. It's going to be a little bit more difficult. I try to work the more difficult ones in the examples so that you can tackle the easier problems on your own. When I say easier, I don't mean easy. I mean easier than some others, which is relative. I find transformations to be quite hard. When we're looking at number 27, we're starting with the toolkit function, which looks like this. Do you remember which one this is? Yep, it's x cubed. So our toolkit function is g of x equal x cubed. Remember that this has the basic shape where it comes up, flattens near the origin, and then continues up. It hits the origin at 0, 0. It hits the point 1, 1. It hits 2, 8 up here, -1, -1, and -2, -8. This is our toolkit function. Now what's happened to it? It's been transformed so that we have y equals f of 2x plus 2. What's happened? Well, the plus 2 is outside of the notation, so we know this is an up 2. The 2 is being multiplied by the x inside the notation, so it's got to be a horizontal stretch or compression. Because it's horizontal, it does the opposite. It's bigger than 1, so I would expect a stretch, so it must compress. This is a horizontal compression by a factor of 2. What's that going to do? It's going to take the x coordinate and cut it in half. Then it's going to take the y coordinate and shift it up 2. When I look at my basic points, 0, 0, if I cut the x coordinate in half, half of 0 is still 0. And then it shifts it up 2. So 0, 0 will go to 0, 2. Let's look down here at our graphs and see which ones have that point. A and B didn't go up 2, they went down 2, so they have to be incorrect. When we're looking at this one, we're looking at the one that has to go up 2. Sorry, lost my focus for a minute there. It's got to be C or D. Now we have a horizontal compression. Horizontal compression. Compression means to push in, like the scene in Star Wars where Han and Luke and Leia and Chewbacca are inside the trash compactor and the walls are coming in. That's a compression, a trash compactor. So the walls are coming in horizontally, which is going to have the effect of stretching the graph vertically. That looks more like problem number D. They both go through 0, 2. We could take a look at another value like 1, 1. When we cut the 1 in half for the x change, it becomes 1/2. And then the y value, instead of being at 1, shifts up to 3. So we would have 1/2, 3, which does match here, but does not match the graph for C. So it must be D. Let's look now at the next one. This is the toolkit function of the square root of x. This is part A, and now we're looking at part B. When we look at the toolkit function, which is the square root of x, we can remember that we have the basic points starting at 0, 0, and then it goes like at the upper arm of a sideways opening parabola, or like someone swimming doing the American crawl. Right 1, up 1, right 4, up 2. That's our toolkit function. What happens when it gets transformed in such a way that we have g of 1/3 x plus 1? We know the plus 1 is outside, so this is a shift up 1. Then looking at the 1/3 x, it's multiplied by x, so it's a horizontal stretch or compression. It's less than 1, so I'd expect a compression, except it does the opposite for x always. So I get a horizontal stretch by a factor of 3. That means each x coordinate gets multiplied by 3. Let's look at our graphs now and see which ones went up 1. This one up 1 and this one up 1, but this one went down 1, which has to be incorrect, and this one left 1. C and D are out. It's got to be A or B. When we're looking at this one then, which one has the horizontal stretch by a factor of 3? What would have happened to my points? 1, 1 would have shifted up 1, so the 1 would have gone to 2, but the x coordinate would have been multiplied by 3, so it would have been 3, 2. Coming to the right, 1, 2, 3, and shifting up 2 tells me that graph A is correct. Graph B, on the other hand, shifting right 3, up 2, misses the mark. It's got to be graph A. Let's now take a look at problem number 28. We have one basic type of problem left to do. 28, 29, and 30 are similar. When I'm looking at problem number 28, I have a transformation of a function which looks like -7 times f of x minus 3. I know the minus 3 has gone down 3, which is affecting the y value. The 7 is also affecting the y value. The 7 means that it has a vertical stretch by a factor of 3, which means I multiply the y value by 7. Oops, did I say 3? I meant 7. What about the negative? The negative is also multiplied by the f of x, the notation or the main operation, which means that this is a vertical reflection across the x-axis. That means the y values get multiplied by a negative. Let's put it all together and see what happens to the point -8, -5. What does this get transformed to? Won't be equal, but it's transformed. Well, we know, for example, that the first thing we want to do is we want to stretch it vertically by a factor of 7. We always have to do the multiplication parts before we do the addition subtraction. So we do the 7 times -5, which gives us -35. Then we reflect it by multiplying by a -1, which gives us 35. So our first thing is the vertical stretch, which makes it go to -8, -35. This is the vertical stretch by a factor of 7. Then we do the reflection, which sends it to -8, 35. Finally, we do the shift down 3, which subtracts 3 from the 35 and sends our point finally to its final resting place at -8, 32. I think the transform point is going to be at -8, 32. Let's check and see. Love the green checks. I find these problems to be quite difficult. And keep in mind that I also think algebra is the most difficult mathematics that we teach at Red Rocks. So you're doing one of the hardest things in one of the hardest subjects. Don't worry if you struggle with this. Struggling with it is normal. Most students struggle with it. It takes a while to get this down. I've been doing it a long time, and even I still struggle sometimes. Let's take a look at the next problem. In problem number 29, we have the point 2, 2, and it's on the graph of the original Toolkit function. We want to know where it gets sent in the transformed equation, which is y equal f of -10x plus 7. Now, when we're looking at this part right here, we have to think about what gets done first. Notice that the things inside notation affect x. So what is happening to the x? First, it's being multiplied by 10, which is a number larger than 1, which is normally a stretch, but it's affecting x, so it's actually a compression. The 10 is a horizontal compression by a factor of 10. That means that the x coordinate gets divided by 10. Then what happens with the negative? Then it gets multiplied by a negative, which will change it as a horizontal reflection across the y-axis. Finally, the last thing that happens is that the y value is shifted up 7. That's a vertical shift up 7. That affects the y value. Let's now take the point and transform it one step at a time. The first thing we want to do is the horizontal compression by a factor of 10. It's the closest to the x. So 2 gets transformed. I take the x component and I divide by 2. So I get 2 divided by 10. Did I say divided by 2? I meant 2 divided by 10. And I leave the y value alone. This is the horizontal compression. By a factor of 10. I can also rewrite this as 1 divided by 5, since that's equivalent to 2 divided by 10. That's simply simplifying the expression. The next thing I want to do is the horizontal reflection across the y-axis. Then I multiply the x component by a negative. That gives me -1/5 2. This is the horizontal reflection across the y-axis. What about the last step? The last step is the adding 7, which is the vertical shift up 7. Vertical shifts affect y, so I add 7 to the 2. Two plus 7 gives me 9. The final transformed value is -1/5, 9. Let's enter that in and see if we've got it right. Perfect. The last problem is similar to the ones we've done previously, and I'll leave it to you to practice on at home. I know this has been a really long and really difficult section. Allow a lot of time to work through these and only work at most 2 hours at a time. After 2 hours, we all kind of go a little brain dead. You need to take a break and do something mindless. Go for a walk, play with your dog, do some laundry, maybe clean up some dishes. That's the kind of mindless thing we want to do. Get your mind off the mathematics for a while. Studying something else probably won't help. Then come back to it after 30 minutes and tackle it again. I hope this helped in this very, very difficult section. And I'm sorry the video is so long.